All right, so we are going to now get into Taylor and Maclaurin series of some known functions and how those get generated. So a Taylor series is centered at A, and basically what he found out is if you have any function, okay, and you find the point A, f of A, that we can then find the equation of the tangent line to the curve, and that would be a 1-degree polynomial, if you will. So the point itself is a 0-degree polynomial. They already intersect at that point. A degree 1 polynomial would be the line, and it just so happens that that's f double prime of a x minus a. Think about point slope form. Right, if you add y1 to the other side, that's the same thing as finding the slope of the tangent line and then plugging into a f of a, okay? But he took it even further than that. So that's kind of more like a Cal 1 topic. He said, well, let's find a degree 2 polynomial, and how do I figure out the curvature that I need for that quadratic to happen? And so he's like, well, if I take the second derivative, that's going to give me concavity at that point. But it wasn't exactly just that. It had to be over something. So he figured out it's over 2 factorial. Okay. And then if you wanted to use a cubic function, then you're going to find the third derivative at that point and put it over 3 factorial. And that's going to find your cubic function. And so these are all of the partial sums for the point, first, second, and third Taylor polynomials. And if it's centered at 0, we call that the Maclaurin series, okay? So let's do this for natural log at x equals 0. So let's look at our natural log function. So p of 0 is just f of 0. And so that's natural log, so p of 0, excuse me, we're centered at 1. So p of 1, natural log of 1, which is 0. All right, p of 1 is then 0 plus f prime at 1 times x minus 1. All right, so what's the derivative of my function? F prime is 1 over x. So f prime at 1 is 1, and so this is going to end up equaling 0 plus 1 times x minus 1. Let's say I want to figure out a second degree polynomial. So p2 is all of that, 0 plus 1 times x minus 1. But then I need to add the second derivative at 1 over 2 factorial x minus 1 squared. All right, so what's the second derivative? This is x to the negative 1. So the second derivative is negative 1x to the negative 2. I'm still plugging in 1 though, so this is going to end up being 0 plus 1 x minus 1 plus negative 1 over 2 factorial x minus 1 squared. All right, let's figure out P3. So P3 would be all of this plus the third derivative at 1 over 3 factorial x minus 1 to the third. All right, so the third derivative, negative 2, bring it down 2x to the negative 3. I'm still plugging in 1. And so this right here ends up being 2. All right, then we can also, it says use a graphing utility to look at this. So let's pull up a graph. Y equals natural log of x. Our first point was y equals 0. It's only going to be intersecting at that point. But then we said plus 1 times x minus 1. Okay, so tangent, and we could zoom in. In fact, I'm going to move my center so we can see it right there, and maybe I do zoom in a little bit. Okay, so converges for more than just the point, if you will, like it models the function for a little bit of an interval. And then what do we have after that? Minus 2 over, what was it? Minus 1 over 2 factorial. 2 factorial x minus 1 squared. Okay, we can see, yep, it still is tangential at that point. It still intersects only at that point, really, but it models for a little bit longer. All right, then it was plus 2 over 3 factorial x minus 1 to the third. Okay, a little bit better. Okay, and so we can see as we look at those partial sums, whereas we're increasing our polynomial degree, we're getting a better approximation of the natural log function over time. All right, let's go ahead and look at one more example. So let's also do 1 over x at x equals 1. Now for both of these, we can't do a Maclaurin series because we can't center them at 0. Both of these functions aren't defined at 0. So we're going to actually find, and we're going to discover the Taylor series at x equals 1. So here's our graph, right? So our first one is a degree of nothing, so it's just 1. Let's see, P1 is then 1 plus, what is the derivative there? So f is x to the negative 1. So f prime is negative x to the negative 2. And I'm plugging in 1, so it's going to be negative 1 x minus 1. Well, that makes sense. That's negative x plus 2 as a line. And if you were to take that out, you would end up getting negative x plus 2. All right, what's f double prime? That's going to be positive 2x to the negative 3. So plus 2 over 2 factorial. Oops. Let's write that as its own line. Sorry. So that we can see the pattern here. P2, 1 plus negative 1x minus 1 to the 1 plus 2 over 2 factorial x minus 1 squared. The third derivative is negative 6x to the 4th. So it's all of that plus negative 6 over 3 factorial x minus 1 cubed. I think I can figure out a pattern here for this. So it looks like I always have the n, whatever n is whatever my last term is. So if I need to figure this out and I'm going from n equals something to infinity, it looks like I'm always going to have an x minus 1 to the n for whatever number I'm on. So when I plug in 1, I have everything at 0 and 1. When I plug in 2, I have 0, 1, and 2. So that's going to be important there. I do have an x minus 1 to the 0. I would just not write it. So it looks like I'm going to start at 0. And then it looks like I'm going to end up having an alternating piece, right? I have positive, negative 2 over 2 factorial is 1. Negative 6 over 3 factorial is negative 1. So in order for this to be negative, positive, when I plug in 0, I get 1. When I plug in 1, I get negative 1. Okay, so to the n. And then I think that's going to be it, right? That's going to be it. All right, so now let's find the interval of convergence. So limit as n goes to infinity, negative n to the n plus 1, x minus 1 to the n plus 1, all over negative 1 to the n, x minus 1 to the n less than 1. These don't matter, and I end up with no n's, so I'm really just looking at when is x minus 1 less than 1. Well, this makes sense because my center is 1, right? So center is 1. Radius is 1. And so I can set this up as negative 1 less than x minus 1 less than 1. And if I add 1 to both sides, I get 0 less than x less than 2. And again, with a center at 1 and a radius of 1, that makes sense that I'm looking at like 0 to 2 for my interval of convergence. So this is only good on my graph. Well, that makes sense. I can't go past 0 because it's not defined, right? And then 2. So let's see. If x equals 0, can I let x equal 0? No, I cannot. But let's go back up into our thing here. If x is 0, then I end up getting positive 1 to the n, right? X equals 0. Then I end up getting negative 1 to the n times negative 1 to the n, which is just always positive 1. Added, 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 added. Not convergent there. If I have x equals 2, then I end up having negative 1 to the n, positive 1 to the n. This is still divergent, okay? You have negative 1 and then 0, and then negative 1 and 0, negative, like that's just going to be divergent. So this is going to be my final answer. For my interval, we are not convergent at 0. Makes sense, but also not convergent at 2.